All right. Okay. So basically, when we want to perform the simulations, first you need to get the dynamic model. All right. So let's say right now, we have a very simple dynamic equations. I think everyone in the control engineering has already learned how to develop the mathematical model for this spring mass system. Right, so we have a spring and then a mass. Then the mass is sliding on the surface at the with a certain kind of frictions, and the friction is having a column frictions, which is a mu. And then assume that the mass is equal to 1 kilogram. The spring stiffness is equal to 3, and then the friction coefficient is equal to 0.2. And therefore, from the formulation from mathematical modeling, and we could get the equations as shown over here. There is the dynamic equations, right? Where we apply a kind of a force over here, and then the spring mass system, right? So it will form this kind of a very general mechanical equations. All right. Okay, so there is the first step. After when we need to get the mathematical model, and once we get the mathematical model, and let's say if the input ft is actually a sine wave, okay, a sinusoidal force with the a sine 2 pi 0.1 t, and a is the 3. It means that it is actually a 3 newtons. It fluctuates around the 3 newtons, okay, plus minus 3 newtons at the frequency of 0.1 hertz. And what is the simulations outcome for this dynamic model? Okay, we want to simulate and then see what is happening to the mass, and then the movement of the mass over the time after we apply the input force, the sinusoidal force. All right. So everyone, so far you clear about the questions, right? Okay. And therefore, the first step that we need to do in order to, before we could put it into the MATLAB Simulink, right? So first of all is that we need to rewrite the system, rewrite the dynamic model, right? So that we can get the accelerations. Okay, the highest order of the differentiation, which is the acceleration, and therefore we need to rewrite it such that d squared x over dt squared is actually equals to f and then minus 0.2 dx dt, okay, and then minus 3x. Right, so that is the first step. We need to write the dynamic model to give us the accelerations. And once we have these accelerations equations, and now we are able to put it into the MATLAB Simulink. Okay, and now let me show you the MATLAB Simulink. Okay. So let me share the, I think just share the screen. All right. So you can see there is the MATLAB Simulink. Okay, so you may now open up the MATLAB, and then later on to initiate the Simulink, just click on this button, Simulink. And then just wait for a moment. Usually this could take quite a long time, right? And once it has been initiated, then go to this blank model. You just click at the blank model to bring out the blank workspace. All right, and this could take a very long time. If let's say your computer is actually not very fast, then just wait for a moment. All right. Okay, so up to now, everyone, you still with me?
Yes, sir.
All right. Okay, so you can see that this is taking a very long time to process. All right, so this is basically the workspace, okay, which is blank. You can see that everything is just a white color. Okay, so to bring out the all the toolbox, all the blocks, you can go to this library browser. Just click on that, and it will bring out all these toolbox that has been installed to your MATLAB Simulink. And you can use all these toolbox in order to run the Simulink. Okay, and basically, the most often toolbox that is that are going to be used is actually this one, the Simulink, right? So for this Simulink, and you can see that under the Simulink, you double click and it will bring out all these tools, all the blocks, right? And continuous, if you take a look on the continuous, right? Let me see, can I zoom it? No, I can't zoom it. All right, fit to view, no, okay, anyway, you'll just take a look on your own screen, right? After you bring out this, you can pull down the continuous, and this continuous basically have all the blocks, essential blocks for the to perform the differentiation and also the integrations, right? For example, over here, derivative, this is the block that we can differentiate. And then later on, we have an integrator, 1 over x. And using these blocks, we are able to integrate, right? Other than that, we have a state space equation. If let's say you have a state space equation, then you can put it in. And if you are using the transfer function, so this is the blocks where we can put in the transfer function. All right, so this is one of the most commonly used blocks. And then later on, we also have discontinuous. Discontinuous is usually used to model something that is non-linear. So for example, the frictions, we can use this, and also the net zone. And then later on, the saturations. These are all the blocks that are commonly used in order to model the non-linearities inside the system. If let's say you are using a discrete system, right, you model your time equations into discrete equations, then in that case, you will be most often you are going to use this discrete. Right, for a discrete system, it will have different differentiation approach. So we can differentiate using this difference or this discrete derivative. Discrete derivative is more appropriate compared to the difference. Difference is too crude for the differentiations. And then we can also have a discrete state space model, discrete transfer functions, and also there is a discrete integrator. Right, discrete integrator, if I'm not mistaken, yeah, it's over here, discrete time integrator. All right, we can integrate using this for a discrete system. Then later on, we have the lookup tables, mathematical operations, which can be used to perform the mathematical calculations, right? And then matrix operations, right? So basically, these are all the essential blocks that we are going to use in order to run the Simulink. All right. Okay, so now let's going back to this dynamic equations, and we are going to model this to create the blocks for these dynamic models. Okay, and now let's take a look. Okay, so the dynamic equations is d squared x dt squared. So first of all, we need to do f minus 0.2 ds dt, right? So f minus, so this is a minus, and therefore we just get math operations and then get the add blocks, right? So you just click and then drag to this white space, and then it will these blocks will appear. Okay, and then later on you just double click on it and then plus minus. So we are going to write the equations f minus 0.2 time ds dt. Okay, so here is f and then minus 0.2. So we need to have a 0.2. We can have again, right? So just drag in the blocks again and then double click and change the gain value to 0.2. Okay, and therefore the velocities will multiply. Over here there is a dx dt coming in. Okay, so here it will be the ds dt. Okay, create a notation. So this is dx dt. All right, so ds dt will comes into in this arrow. As for here, it will come in. What it is expected is actually the f. So f minus ds dt. Okay, so you all could see this clearly, right? That is the f and then minus 0.2 times ds dt. Okay, so far everyone? Are
Yes,
you
sir.
clear? Yeah. Any question? No question?
One question.
Yeah.
Okay, so the plus and minus box, the idea is that both of them come into it, and then you add the f, and then you subtract the dx dt multiplied by the gain 0.2.
Yes. So you need to
Should
know that in the Simulink, the calculations, the sequence of calculation is actually from left to right. Okay. So what is at the left will be calculated first. So in that case, this will comes, you can see it from left to right. So first of all, you will encounter this 0.2. All right, so 0.2 will multiply to this ds dt and then get some value and then store it here. All right, and then later on comes to here, it encounters the summation blocks, and therefore it will perform the summation, which is the f minus this value. Okay.
Okay.
All right.
Because I was wondering, how do we know which one goes first?
In Simulink, it's from left to right. It's always from left to right.
Okay.
Okay, so left to right, it doesn't mean that, for example, if I put the blocks over here, then this gain will becomes more to the right. Okay, so it actually look at the Simulink by itself will look at the sequence. Okay, and then it will arrange the blocks according to the sequence. All right. Okay, so we have already performed f minus 0.2 times ds dt, and then we are going to minus 3x. Okay, minus 3x. So in order to get this minus 3x, right, we can double click on this add box and then add in another minus. So in that case, we are going to get a plus minus minus. All right. So once we are we have gotten this, then the equation is actually minus 3 times x. Right. So minus 3 times x, again we get a gain. Right. And this gain is having a 3, and we want to multiply. This is expecting to get the input x. So 3 times x, and then later on we'll minus to here. Okay, so in that case, plus minus minus, we have already performed f minus 0.2 ds dt minus 3s, and the outcome of it will be d squared x dt squared. And therefore, the outcome from here, outcome from this plot, it is actually the d squared x over dt squared. That is the acceleration. Okay, clear?
Yes.
All right. So now once we have already gotten this acceleration, and the next step will be to perform the integrations. So we can go to the continuous simulating continuous block, and then you drag in the integrator, right? There is a 1 over x, and then we just put the integrator over here. Okay, yeah. Okay. So in that case, after we integrate one times, what we are going to get over here will be dx dt. That is the velocity. And then later on, we need to integrate again. And to integrate again, we just drag in the integrator block again. Or you can duplicate, right? To duplicate a block inside this white space, you can right click and then copy, or you can also right click and hold. Okay, right click and hold, and then you drag, then it will straight away duplicate the block for you. All right, and you can see that initially the name for this block is integrator. After you integrate, you will automatically assign integrator 1. All right, and then if you duplicate more, then you are going to get integrator 2. All right, so you can duplicate any blocks just by right click and hold. Do not release the button. All right, so just click, right click, and then hold and drag, and you can duplicate any blocks. Okay, and now just put in and integrate again. What we are going to get over here is actually the x. All right, so in that case, so now we can see that over here there are 3 inputs that is left hanging, and therefore we need to tell the Simulink where exactly we can this x, ds, dt, and f is coming from. All right, and therefore this ds, dt, and the x is actually over here. All right, we have a ds, dt, and therefore for the x, right, and for the s, we need to create a branch and then feedback and then enter over here. All right, and then to do so, you just simply right click on the branch, right click, and then you can drag an arrow coming down. Okay, right click and then hold, and then later on you can just put it here. Okay, and you have already created the branch. There is the x. Right, and for the velocity is the same thing. The SDT, just right click and then hold, and you will come out with the branch, and then later on just put it here. Okay, and you can rearrange the arrow to your likes. Okay, so you can see that now all the arrow is a black color. So that means it is correct. Okay, we have already introduced to the MATLAB Simulink where exactly is this DSDT and the X. And there is only 2 arrows hanging over there. So X is actually the values that we want to monitor, right? And to monitor the X, we can simply drag in a scope to give us some kind of a plotting of the graph, how is the X is looking like. And therefore you can go to the sinks. Okay, sinks, and then here you have all the output display, and you can see that we have a record, scope, out one, display, and so on. So we are going to use the scope, right, and just click the scope over here and then pull it here. Okay, so by using the scope, we can visualize how is the outcome or the time response of X over the time. Okay, as for the F is actually is equations a sine 2 pi 0.1 t, and you can see that it is expecting to have a time, and therefore we need to create a time to extract the time element inside this MATLAB Simulink also, right? So in that case, we need to go to the sources. Sources is actually all the inputs user that can input to the system, and then the MATLAB Simulink will use these inputs, user inputs to perform the calculations. Right, so from the sources, you can get the time. Right, time is one of the element that is essential in the calculations. The element, where is it? Yeah, it's a clock. Right, you can get the clock. This is actually the time. Okay, the t. And then later on, this one we need to perform the functions. Okay, to do the calculations, and therefore you can go to this user-defined functions. Okay, to add in the equations to perform these calculations. All right, this equation a sine 2 pi 0.1 t, a is equals to 3. All right, so to perform that mathematical calculation of functions, right, we can just use these functions, right? So you just add it in, there is the function. Okay, and then later on put it here, and we can complete all the connections. Right, so time will enters into here, and then to calculate for the f. All right, and inside the functions, right, we need to write in the equation, which is a times sine 2 pi and then 0.1 times t. That is the equations. Okay, and we know that for the a, the value for a is actually equals to 3. All right, so that is equals to 3. And then sine 2 pi, in MATLAB Simulink, pi is equals to 3.142. And therefore, you can just safely type this pi without define the value, because by default, MATLAB already assigned pi as a 3.142. Right, and then 2 pi and 0.1 t is that is the clock. Right, clock is actually the input to the functions block, and any functions you can see that use u as the input variable name. So u is the input to the function blocks, which stands for the time. Okay, and therefore this should be looking something as this. Right, the clock, which is the time, it enters as the u is a function of function of time. All right, in this case, because time is the input, and you just type in this function 3 sine 2 pi 0.1 times u. Okay, so that is pretty much the simulations. Okay, and now you can see that over here there is initial conditions for the velocity. Initial velocity we will just set to 0. Initially everything is just starting from 0. X is also initially is 0. Okay, and once it's done, and we can now start the simulations. So let's say we want to simulate for 10 seconds, and you may just click on this run button, and you can see that there is the indicator, and then yeah, ready. It means that the simulation is already done. And once the simulation is done, you may double click onto this scope, and it will get a printing a time scope of the simulations X. Okay, so this is actually the outcome, the response of the X. So it means that the max block is initially at the 0 position, will move to the 1.5, and because of the spring will pull it back, and then later on it will start to compress, go to the negative 0 point, and it will just keep on oscillating. Okay, right, and because of the frictions, this doesn't forms a very complete pure sine wave. So this is a simulation taking for 10 seconds. 10 seconds, it seems like it's too short in order to see the response. So maybe we can increase it to 50 seconds, and then we can run again and double click, and you can see that this actually gives us a sine wave, and it just keep on integrating, right? And to reduce this oscillatory time, maybe we can increase the frictions. Oh no, sorry, because of the force. So because of the input force, so it will just keep on oscillating. All right, everyone.
Yeah.
Okay, so you all get the same result as mine.
Stop.
Similar.
Similar. Okay, so that's good. So you all is able to follow this kind of speed, right? Am I going too fast so far? Okay. All right. That is pretty much about this system, this example. May I proceed, or you need some time to try this out? Everyone, should I proceed?
Oh, yes, Doctor.
Okay, so I think I'll just proceed. Okay, so that is the first example, very simple example. All right, so now let's take a look on this second example. Right, we have a cup pendulum system as shown over here. Right, everyone already seen in the lecture notes, and we can see that these cup and pendulum systems can be modeled through this Lagrange-Euler formulation approach. You can mathematically obtain the mathematical model for this cup system by using and then you can compute and get this dynamic model. Right, so this dynamic model, we write it into the form of a matrix. It gives us a 2 times 2 matrix. That is the inertia matrix. As for this one, this is the Coriolis factors, and then combined with all sorts of disturbance and also the potential energy functions. And yeah, I think also the mg, so there is a gravitational effects in it as well. Right, so that is the dynamic equation model, and given that m is equal to 2 kilogram, so the mass for the cut is 2 kilogram, and the mass for this pendulum ball is 0.5 kilogram, and spring stiffness is actually 10 Newton per meter, and the length of the cable is 0.5 meters, and the frictions at the cut is 0.7, and therefore determine the time response of this system. So note that the system is disturbed by initially shifted the mass m to 0.3 m and theta equals to 0 radian. So what it means over here is that this example is different from the example just now. Example just now, we introduced actuation force F, which is a sinusoidal actuation force to actuate the system. So in the previous dynamic model, we have external force. But for this cup pendulum system, you can see that we don't have any external force. So all the external force applied onto the system is basically zero. And therefore, how we could break the balance? So we could break the balance by setting the initial conditions, right? So it means that, let's say initially this is at the zero positions, right? This is the zero positions, and therefore we just shift this mass block. Initially over here it said that by shifting shifting the max to 0.3 meters, theta and 0 radian. So it means that initially we shift it to 0.3 meters. And this theta, we are not swinging it, right? So we just simply set this to be 0. So it means that it is hanging. It is actually pulling down and then not moving at all. So there is the initial conditions for this max cut system. Okay, everyone clear about this question, right? Is that okay? Clear? All right. So I'm now going to perform the dynamic equations. The computations in form of a matrix, because when we are running the MATLAB Simulink, it's actually much more convenient if we run the simulation in the matrix form. Okay, so first you rewrite the dynamic equations into the matrix form as this, with the accelerations at one side, and then there is at another side, and then later on we try to derive very similarly, we try to derive s double dot and theta double dot. All right, so s double dot and theta double dot at one side, this is basically equals to, right? So in that case, we can see that this one will come to here, and then later on we have an inverse matrix, right? So inverse matrix, the inertial matrix, right, which is here. This is the inertial matrix, right? Okay, so this is the inertial matrix, and then we inverse it and multiplies to this B matrix. Let's say this is the B matrix, which is actually the negative B. Okay, so this shift one side is a negative B, and then we multiply with the inverse matrix. So that is basically the whole equations that we can use to run the simulations. Okay, so now let me delete all of these blocks, and then we start from scratch again. Okay, so the first step that we are going to do is we create the matrix, right? First of all is that we need to create the matrix. So to create the matrix, right, you can go to the, again, library browser, and then here under this Simulink, you go to user defined functions, right? And then you can get in MATLAB functions. Okay, so MATLAB functions, you drag in. There is the MATLAB functions. Okay, and you double click these MATLAB functions, and you are going to get something as this, right? That is y is equals to function of u. U is the input, y is the output, and by default it is programmed as y is equals to u. All right, so now I'm going to use these MATLAB functions to construct this inertial matrix, right? So to construct this inertial matrix, okay, so first of all is that, all right, let me rearrange this one. Okay, okay, so we have several constants, right? So I'll just say m is equals to 2 kilogram. Yeah, okay, and then the small m is equals to 0.5 kilogram, and then k is equals to 10 Newton per meters, and then L is equals to 0.5 meters, and then mu is equals to 0.7. These are all the constant. All right, so to put it in one line, Right. Usually for L, I think it's better just use a capital L lah, right? Or else the L will looks like 1. Okay, could be a little bit confusing. Okay, so these are all the constants that is involved in the equations. And then to construct the matrix, right? So this matrix will be inertia, right? The inertia matrix is actually equal to create the matrix in MATLAB, we are using the square brackets, right? So for the square brackets, we have this 2 times 2 matrix. So first of all is m plus m for the first element, right? Which is here. This is the m plus m. Right, and then the second one will be the ml cos theta, which is this one. All right, so for the ml cos theta, we have m times l and then times cos theta, right? Okay, so theta we put as a th. Later on, we'll define where is this theta comes from. Okay, and then later on, we want to define this second row, first column, which is also ml cos theta. And then to define it, we use a semicolon. This indicates that this goes to the second row. Right, so second rows, we also have m times l times cos theta. Okay, and then later on, the second row, second column, we have m times l square. So in this case, we get the in. Okay, so far so good. Everyone? Is that clear? Clear, right? Okay, so now you can see that here the output will be produced. Output we want to produce to provide is actually the inertia, and therefore instead of u, we just put y is equal to inertia. Okay, so in that case, we have already obtained the inertia blocks. All right, and to go out, we can just click this bed, and we come out as here, right? And we can actually instead of naming this block as a MATLAB functions, we can name it as inertia, right? So you just simply highlight here, and then you type in. So in that case, we know that this is basically a block that calculates for the inertia. Okay. All right. So now let's come back over here. And if we take a look inside these dynamic equations, and we can see that there are several variables that needs to be used in order to calculate for this inertia matrix and also these B vectors. Right, so what is needed is the theta. So we need theta. And then over here, we need theta dot and then s dot and also the s and also theta. So in other words, later on, we are going to feed back the value that is needed for the calculation will be theta dot. Okay, I think I'll just arrange it in sequence, right? So value that needs to be feedback will be s dot, right? Which appears over here. We need s dot in order to calculate for these inertial functions and also the B function. And then later on, we also need x, right? So we need the x value. And here for the inertias, it only requires theta, right? Because all the others are just constant, it only requires theta. but B requires theta dot also. Right, there is a theta dot, and then later on it also requires theta. So that means we are going to create these vectors for the feedback, okay, and use as the input into these inertial blocks and also the B blocks. Okay, so this is the four variables that we are going to take using, and therefore x dot will be referred as the U1, x will be the U2, theta dot will be the U3, and theta will be the U4. Okay. All right. So in that case, we just follow these arrangements. Okay. These are the first assumptions I made for the feedback signal. Okay. First setting. All right. So s dot, x, theta dot, and theta. So now let's go back to these inertial blocks. It will be receiving just now, this u will be that 4 times 1 vectors s dot, where okay, I think I'll just make a comment. So for the comments, you can comment using the percentage. So in MATLAB, percentage, it means the comment. And so u is actually a vectors of x dot, and then x, and then theta dot, and then the theta. So that is the u, right? So here I only comment. Comment is just for our own reference, for us to know that what is u. And it will not be used in the computations follows on. All right, so this one basically is not needed. You can erase it, but I just put it here to tell you what is this u. Right, so in that case, we may now relate this inertia matrix to the inputs, right? So inertia, it requires m and m. This one is constant. So only theta is the variable. That is the input. So from here you can see that it is actually U4. Okay, so we just replace th, the theta, as the U4, and here again ml cos theta again is U4. Right, m is constant, l is constant. Okay, so in that case, we have already done. All right, everyone? Is that clear?
Yes, doctor.
Okay. All right. This is the MATLAB program, right? How we can set up for the inertia matrix. But for the Simulink blocks, we also need to adjust the setting. So to adjust the setting, you need to go to here. There is the edit data. We need to inform these MATLAB blocks what is the dimension of the input signal and also the output dimensions. All right. So you just go to here and then click onto this edit data, and it will come to here. There's the site. Okay. And then you can see that at here. So now we are going to click U, which is the input, right? Click at the U over here, it gives us the input, and you can see that here we have the port 1 scope, there is the input, and then the size, right? For the size, just now you can see that it is actually here by default is -1. -1, it means that there is no setting, and therefore we need to put in the size, right? So for the size, this is actually equals to input u is a 4 times 1 vectors, right? So 4 times 1, it is the size will be 4 rows and then 0 columns. Okay, so that means this is actually vectors, 4 rows and 0 vectors. Okay, so that is for u. The size is 4 and 0. and the output from the Y, and you can see that this is actually a 2 times 2 matrix, which stands for, so the size will be 2 rows, 2 column. Okay, so for the first input is actually 4 times 1 vectors, and output Y is 2 times 2 matrix. Okay, so by doing so, we are done, and we can go back now. Right, so just going out. So in that case, we have already set up these inertia matrix blocks. Okay, and we do the same things for the B blocks. Okay, so we tag in the another MATLAB functions, and this is actually the B blocks. Okay, so for the B blocks, double click, and you can see that by default it is still Y is equals to U. That is the default. Right, so I think I'll just close all these. Okay, and then minimize, and we are now trying to program this B matrix. So again, we add in all the constant. M is equals to 2, M is equals to 0.5, and then K is equals to 10, and then L is equals to 0.5, and then later on mu is equals to 0.7. Okay, and now B matrix is actually equals to, you can see this is 2 times 1 vectors. So for the first row, we have negative m, so this is a small m times L times, and again here U, we know that what we are going to fit into the blocks for the U is actually the 4 times 1 vectors, which stands for x dot, and then x, and then theta dot, and theta. Okay, so that is the signals that has been feedback, and then we can we use it as the input to the B blocks. Right, so negative m times L times theta dot. So theta dot, you can see that is actually the U3, right? So we have the U3 square. So U3 square, so we can just type something as this, U3 times U3, which is the theta dot square, and then later on times sine theta. So sine theta, we know that theta is U4. All right, so here we have already completed to here, and eventually we also have a plus mu, and then times x dot. X dot, we know that is a U1, and then plus K spring stiffness, and then multiplies by the x. X is U2. Okay. And then later on, for the second rows, we have M times G. So G, we can define it G as G is equals to 9.81. Okay, so M times G times L, and then times sine. Theta is U4. Okay, so in that case, we get the B. There is a B vectors, and then the output, we change it to B. We are outputting the B. Okay, everyone? Is that clear?
So we need to give the size of this also.
Yeah, This one, so up to now, everyone clear, right? You understand, right? How to program for the B matrix. Okay, so there is the equations, and then now we need to define the size, the dimension of it. So again, you just go to edit data, and then you just click at U over here, and you can see that the size. And basically, the size for the input is a 4 times 1 vector. So we have 4 rows and then 0 columns. Wait, sorry. 4 rows, 1 column. Yeah, it's actually it's a 1 column. Yeah. 4 rows and 1 columns. And then the output y is actually, it becomes it's a 2 times 1 vector, so 2 rows and then 1 column. Okay, so 2 times 1 and 4 times 1. 2 times 1, 4 times 1. All right. So yeah, I think there is a mistakes I've made. For the inertia again, yeah, I think I need to change it. So U is 4 times 1, not 4 times 0. Okay, so there is a 4 times 1, 4 rows, 1 column, and then Y is 2 rows, 2 columns. Okay. So yeah, 4 times 1, 2 times 1. Okay, so in that case, we are already done getting the inertia matrix and the B matrix. Okay, everyone? Shall I proceed? No question, right?
Doctor, can you
Yeah,
go back to the second function, the size?
the B is it?
Yeah. Can you show
B,
again U and Y?
and
The
then the
size.
edit data. U is 4
Oh,
times 1.
4 times 1. Okay.
Okay, 4 rows and then 1 column. Output for the Y is 2 rows, 1 column.
Okay. Thank you, Doctor.
All right. Okay, any more? So you're still with me, or you are still busy typing in all these parameters, constant equations? Okay, all right. So if no questions, I think I'll just proceed. Okay, so if we are now already getting this inertia, all right, and then the B, we also have this B matrix. Okay, so what we are going to do now is that we are going to put it into these equations. All right, we want to calculate for the S double dot and theta double dot. So S double dot and theta double dot basically is inertia matrix we need to inverse. After inverse, we multiply with the negative B. Right, so for the negative B, here we have the B, and then we want to get a negative. So basically, it just means that we are multiplying to a negative 1. Okay, and since B outputting is a 2 times 1 vectors, we are multiplying constants of negative 1 and negative 1. So in that case, we can use these sources, and then we get a constant. So for this constant, we have a negative 1 and then negative 1, which is 2 times 1. Okay, so this one will calculate for the B, and then multiplies with the negative 1. Okay, negative 1. Okay, it seems like all right, it will not show in the vector form. Right, so this is a negative 1 and negative 1. Right, which is 2 times 1, and you can see that is a 2 times 1 vectors. Negative. Yeah, it's just a negative 1. Right, so b will multiply to -1. So either -1 times b lah. Right, so if -1 times b, then okay, I will multiply these two together just to invert this negative b becomes a negative b. And to do so, you go to the math operations over here, and then you drag it down. Math operation. There is a matrix operations. You can double click, and over here, and you can see that there is a multiplications, transpose, symmetric identity matrix. Yeah, I think cross product. Okay, then okay, never mind. It's not cross product. Right. So yeah, I think just math operation. All right. So just go to math operations and look for multiplications. Right. Multiplications. Where is the multiplications? Rounding product. Yeah, I think it's this one, product. There any more? Any others? Dot product. But anyway, dot product and then divide and this product. These are all actually the same, right? So you can see that. Let's say I drag a product and then you double click. So you can see that these multiplications, you can change it to either element wise or matrix multiplication. So element wise and matrix multiply okay, or this dot product and you double click. Okay, it's a little bit different. All right, okay, anyway, I think you just use this product. Okay, product for the multiplications. For the divide, yeah, divide and the product, they are exactly the same. Okay, so you can see that if I want to change to this divide, I just simply wait, number of inputs, you just type star and slash. Right, so this one I just type star and slash, and you can see that this changed into divide. So product and divide, they are exactly the same. Right, so we are interested to get the multiplications, right? So that's why it's 2, right? And then again, this has to be element wise. Okay, multiplication is element wise because we are basically multiplying 2 times 1 and 2 times 1. Okay, so it's a 2 times 1 matrix, and then later on vectors multiplies with another 2 times 1 vectors. This cannot be matrix multiplications because matrix multiplication for this column and the rows, they should be the same. If let's say this is a cross product, right? So matrix multiplication, it stands for the cross product. So this one, you can see that 1 and 2, they are not identical. So that means we cannot perform matrix multiplication. Rather, this has to be element wise, where the first row multiplies with the first row, second row multiplies with the second row. Okay, is that clear? Right, so here this is a 2 times 1. Output of here of B is also 2 times 1, and therefore we element wise multiplications multiply both together, so we still get 2 times 1 as the output. Okay, so this gives us negative B. Okay, right, so for these multiplications, you put as a -1 on top of this B, or B on top of -1. Both are actually the same because this is element wise multiplications. All right, so it doesn't matter which one is on top. All right, but if it is a matrix multiplications, then make sure you need to follow the sequence, right? So for example, right now, this inertia matrix, right? So we have already obtained the negative b, and we need to multiply with the inertia that has been inverted, right? So we need to invert this inertia matrix 2 times, and to do so, you can go to the matrix operations. Matrix operations over here, you can see that there is a inverse matrix square. It doesn't have inverse. All right. Cross product array processing, or is it over here? Inverse mat function square root reshape sign square root. Transpose. Okay. Yeah, so it seems like it doesn't have an inverse. All right. Anyway, we can perform the matrix inverse by several approach. Okay. You can either go to here and then let's see. There's a digital signal processing. Okay, so DSP system toolbox. You can go into here. If let's say you install this DSP toolbox, DSP system toolbox, then you go to the signal operations. So signal operations over here, you should be able to see no, not signal operations. I think it's a mat functions. Yeah, mat functions. Over here, you have a matrices and linear algebra, and you just pull it down, and here you can see that there is a matrix inverse. So matrix inverse provided by this DSP system toolbox, you have LU inverse, Cholesky inverse, LDL inverse, pseudo inverse. So you can use any of them. Let's say I use a LU inverse, which is the most commonly done, right? So in that case, I have invert the inertia matrix. Okay, 2 times 2. After inverse, it is still 2 times 2. Okay. And this is now IN inverse, right? Inverse IN. Right, so the output is actually the right inverse of IN. And now I'm going to perform the matrix multiplication. So again, this multiplication product blocks. So instead of element wise, now I'm going to perform matrix multiplication. This has to be matrix multiplication. Okay, so inverse matrix is having 2 times 2. Right, so 2 times 2 comes from the top, and then output from this negative b is actually 2 times 1. So 2 times 2 times 2 times 1. Right, so this is actually 2 times 2. And at the bottom, it has to be 2 times 1. All right, so this inverted must be on top, because this has to be multiplied with 2 times 1. 2 times 2 times 2 times 1. So that means the column and the rows disagree. So in that case, the multiplication will be success. Okay, everyone?
Yes.
Okay, is that clear? All right, so after multiply, okay, inverted and then multiply with this negative b. So we have produce S double dot and theta double dot. So output from here, it is actually X double dot and theta double dot, which is the acceleration. Right. So in that case, we need to perform the integrations in order to get the velocities. Right, continuous, we go to continuous and then get an integrator. Right, so put in the integrator, it integrates these two variables, s double dot and theta double dot. We are going to get x dot and theta dot. Okay, then we integrate again. In that case, we get x and theta. Okay, everyone? Still with me? Am I going too fast? No? Any question? No question. Okay, so now we are going to generate the input signal. Still remember just now the input signal that we want to we propose to make is actually this one, s dot x theta dot and theta, and then u1 u2 u3 u4, which is 4 times 1 vectors. So in that case we need to generate this signal. Okay, so here we have a s dot theta dot and then s and theta. We need to combine these two together. Right, so the easiest way is actually we just try to break this. Okay, so to break it, you can use the mask. Right, you go to signal routine under this Simulink and then signal routine. So you can see that there is a demask. Right, so this demask will make it break this 2 times 1 and then break it into 1 times 1. Okay, first of all we break them all together. All right, so here yeah, I think I've just put it here. So x dot theta dot after demask. Okay, so in that case what we are going to get over here will be the theta dot. This is theta dot, and then this one is s dot and then theta dot, and from here we are going to get x and theta, which is exactly the same as this sequence, s dot x theta dot, s dot and x theta dot and theta. Right, so that means we need to rearrange it. All right, so it doesn't follow exactly. So this one we are going to get is the x dot, and then here we are getting theta dot. Okay, and this one we get x, and then this one we get theta. Okay, so to combine them into a matrix, we mask it back again, right? So at the signal routine again, and then you go to mask, and then here instead of 2 inputs, you change it to 4 inputs. Right, this is 4 inputs, and now we can make it into the form of sequence. Right, so according to here we have s dot and x, and then theta dot and theta. So s dot comes in here, and then x as the second, theta dot as the third one, and theta is the fourth. Right, so u1 u2 u3 u4, this is the sequence that we want. Okay, and then we are going to make it into this u, and then later on okay, and right, so now we have this u to be feedback. All right, so now that this is the 4 times 1 u, and then later on right click for the branch and then pull it back. Okay, everyone? All right. So we have already generated these 4 times 1 factors and fill it back. And we are now going to create the scope to monitor the output. So just go to the sinks and then we have the scope, right? Just drag in a scope. And this scope, we are more interested to know x and theta. All right, so we can drag this x and theta displacement. We just want to see how is the displacement is over the time. Okay, right. And after that, still remember we need to set the initial conditions, right? So we have a 0.3 and 0. So basically initial condition is only for displacement, it's not for the velocity. Velocity are all equal to 0, only the displacement at set to 0.3, theta is still 0. Okay, so to set this initial conditions, right? So that is the velocity initial condition equal to 0. Okay, and we know that the output is actually 2 times 1, so 0 semicolon and 0. This is 2 times 1 vector. 2 times 1 vectors with 0 and 0 as the initial conditions. Right, and then for this displacement, so initial condition now becomes 0.3 meters. All right, 0.3 meters and theta is 0 radian. Okay, so 0.3 meters, then the theta is 0 radians. All right, so that is the initial conditions. And once it's done, and we may now start the simulation instead of 50 seconds, let's say 20 seconds. Right, we simulate up to 20 seconds, and we may now click run and see how is the results. All right, so it is still compiling. Yeah, ready. So the simulation is successful. So that means I didn't make any mistakes. And you can see that that is actually what we have obtained. Right? So X is the yellow color, the yellow line. And then it actually forms like a sine wave that decays over the time because of the frictions. Right, and also you can see that the blue line, this is the pendulum rotations, the theta, and it is trying to oscillate over the time. And if I increase the simulation time to a longer period of time, let's say 100 seconds, and run the simulations, and you can see that, yeah, because of the frictions, this whole system will eventually converge to 0. All right, so this kind of result, it makes sense to me. Unlike just now, the first example where we have an external force to actuate it, so it will not decay over the time. But this system, because we don't have any external force applied to it, so that's why it decays over time and eventually converge to 0 and reach its equilibrium point. Okay, everyone?
Yes.
All right. So of course, this one, if let's say you are feeling that this graph combined together looks very confusing, you may go to here, the setting. Yeah, setting, and then the number of input ports is 1. Sample time, and then we can change this in order to change it. All right. So this one, okay, this one is cannot. All right, sorry. Go to view, and then yeah, go to view, and then go to layout. Okay, we can have 2 layout. You want to have the side by side, right? Or you can have it to be top and the bottom. All right. So this is we have two layout, and then later on we are configuration going to here. Number of input ports is 1. Layout is changed over here. Sample time. Okay, elements a channel, sample base or a display, active display 1 and 2. So we have 2 signal. All right, so how to break it? Okay. Okay. Style. I think it's the style. Okay, style. It changed the graph. So just now you can see that this line may looks very it's too thin. Maybe you can change it to, let's say, 4 point, and you can see that it becomes bigger in size. That is for the active display 1, and for the 2 you can change to, let's say, also 4. Okay, sorry, active display 1. This one is active display because I changed to two layout. All right, so line, this one is 4, active display is 1. Okay. Yeah. Okay, so if I want to change the blue line, I need to go to integrator, the second output, which is the blue color, right? So this one I changed to 4. Right, so you can see that now the line is becomes dark bigger. All right, so let me see how exactly to number of input ports. Layout, no, not layout. Okay, view, configurations. This configure, not configure. Maybe it's this one. No, wrong. Okay, so elements. Yeah. Layout. Okay. Oh, maximize scanning sample time. 2. Okay. Maybe. Yeah. I think. If let's say we still want to use these 2 layout, and you can see that another way will be we demask the signal first. All right, so here we have already demasked it, and just now still remember for the scope, just now I changed the at the configuration parameters or the setting over here. You just click over here, it brings out this. So input ports, instead of initially it's set as 1, so now I set as 2. Right, layout I put it as this, so you can see that, and therefore after I set to the input ports to 2, so now you have 2 inputs over here. So after demask we have the X, right, and then theta, put it as here. And if I run the simulations, then you will know that this is X and this one will be the theta. Okay, clear?
Yes.
All right, so I think that is pretty much for the demo that I can show you today.